still, because they do a follow-up, which is totally useless, but they do a follow-up and you have to pay for it. It's some taxes. It's 400, 500 euros. I mean, I can even, I don't have enough money for that. Okay. Hi, good morning. It is with great pleasure. Today I'm going to introduce a colleague and I think a good friend of mine, Eric Attias. He is, right now is a million places, University of Texas, Southampton, and also somewhere in Portugal, I think. But Eric did his studies, his undergraduate studies in marine sciences and oceanography in Israel. After that, he just confessed that he started a few PhDs, mostly around biology, but he didn't like it. So finally, he moved to...
I liked it. I just didn't like the lab.
Okay. He moved to Southampton, where he did his master's and a PhD on CSEM, that is the control source electromagnetic geophysical method. That is where he's going to be talking today. Did a postdoc in Hawaii. After that, visiting scientists in Woods Hole Oceanographic Institution with Rob Evans, I think, yeah. And what else? And then, yeah, he got the research assistant professor at the University of Texas in Austin at the Jackson School for Geosciences. Well, Eric,
yeah, that's
the floor is yours.
Thank you, Javi, for inviting me in this nice introduction. And yeah, today, thank you for coming, first of all. And this is kind of a big title, Marine CSEM, which I will show what is it. But how does it interact with the new challenges that we're facing today between the climate and the tectonic that we can image with CSEM, in a way to look at major contemporary challenges, which is mitigating geohazard and new ocean kind of sustainability and resources. So just to put it in a frame of the importance of those kind of topics into climate, I just want to show you something that I really liked, is a National Geographic video, which is in collaboration with a German scientist. This is what we're facing and how the solution might be.
It is 2050. We did not manage to cut emissions when we should have. The very hot temperature means that all ecosystems have been transformed.
Dürre, Stürme, Fluten nehmen in einer Art und Weise zu, wie wir es uns vorher nicht haben vorstellen können.
The vast majority of energy produced in the world still comes from fossil fuels.
Die Welt uneins und die Krise überall.
This is the ex-CEO of Google X, by the way. Yeah, so from here, they're telling us about the alternative ways that we can mitigate those hazards. Obviously, my method is going to solve it all. No, I'm joking. It's just we as a community of geosciences and earth scientists can pull together, and it's all about decentralized, moving to new clean energies and how we mitigate those geohazards. But it's a frame that what might have happened and what could happen if we take actions in time. So when I moved to the Jackson School, after being in Hawaii, I kind of said, okay, I'm going to start this lab of mine, which I call it Ocean Lab, the Ocean and Earth Electromagnetic Laboratory. And the actual vision is to advance the science, but things that kind of correspond or interact with how do we make our environment more sustainable, using the properties of mainly electromagnetic imaging of the subsurface and water column, but with other methods to kind of extract the strength of it. And the vision is to study the interaction between ocean and earth, to mitigate those kind of impacts of climate change-driven phenomena, which is translated to geohazard, and promoting the concept of a new blue economy, which I'm sure in Ocean Institution, you're all aware of that. Now, this is my team in a way. It's important to kind of deviate into two. The core team, it's myself and subsea engineers that have been working for many years in the industry and good friends of mine. And they are the core team that we kind of developing also the next generation of technologies that we would need to face those questions that I will show you later. And obviously with some scientists and postdocs and students. And the entire kind of concept of the lab is to focus on two things: natural hazards and natural resources. And you can see volcanic plumes, continental breakup, subduction, seafloor spreading, or in the natural, submarine, gas hydrate, mineralization, CO2 storage. This is something that I have kind of project in all of them, or head project. And I will focus on a few things that I will show you today and how it interacts and how marine electromagnetic methods are working for that. Now, first of all, besides Javi, I don't know, many people know about marine electromagnetics here and why and how to use it to study the Earth. So think about it. The easiest kind of analogy for it is fundamentally like functional MRI. Okay, it emits it, kind of, it energizes the electrons in our brain, and then measuring back the blood, the flow, the returns of the electrons, and that's translated to blood flow. So in essence, what fMRI is doing is seeing or imaging how fluid flow goes in the brain. This is pretty much the same what we're doing. The physics is a bit different, but it's the same kind of concept. So this is a good video.
Subsurface resistivity from the seabed.
CSEM.
A high-power source of EM energy is towed over a grid of receivers, placed 1 to 3 kilometers apart, at known locations on the seabed. By measuring the refracted energy from subsurface layers, we are able to identify areas of high electrical resistivity, an indicator of hydrocarbons. From one line of receivers, we can image a vertical section with, however, limited resolution and depth positioning. In a 3D survey, a grid of active receivers record both inline and azimuth data. This allows us to map resistivity.
Yeah, you just have a snapshot now. That video was made, remember, when oil and gas was big, but it's just an illustration of how this method sort of work in the field by the company who pretty much leading the industry effort, that's EMGS. Now, the method is kind of divided to two sections, electromagnetic imaging, you would say. You have a passive method, which we call it magnetotelluric, or MT, when we use natural source magnetotelluric feeds that coming from the sun and solar winds, and it interacts with the Earth, and it produces secondary kind of field, which I will explain later, and we record the signal with those electrodes on the seafloor. And then we can interpret them in terms of phase and amplitude. And we have the active system, control source, which is actually energizing the water, that's our source, and we measure the returning signal on those seafloor receivers. Now, the greatest strength of both methods, of the EM method, it's sensitive to volatile temperature and porosity because it kind of incorporates the rock matrix and predominantly sensitive to the pore fluids, while the seismic method, it's more structurally imaging and less on what's within the pore. And why is it important and how it helps us to understand Earth? Because as you can see, the Earth material is sensitive to electrical resistivity, varies between 5 orders of magnitude. So if we have, there is a good distinction between seawater and fresh water, or if you look at the basaltic melt versus partial melt, or hydrocarbons, and so on and so forth. So you get good distinguishing of those Earth materials from the surface to about 200 kilometers, and that with the interpretation of what that kind of conductiveness or resistiveness, which is the kind of the inverse of that, can give us a sense with the interpretation of the geological knowledge, what are we looking at. So a bit about the physics, because you have to understand what you're doing. So basically, it's the decoupled Maxwell equation. When you run a magnetic into a coil, you will get an electric field. The other way around, if you run some energy, some current into iron bar, you will get magnetic field. And that's the Faraday and Ampere's law. If you couple them together, this is basically what happened when we were doing MT imaging. Solar winds, those electromagnetic fields interact with the Earth magnetic kind of magnetosphere, penetrate the subsurface, interact with the core, and what we're measuring, the electrical currents and the magnetic currents. In the active methods, we're using that energy source with that we call it the control, so the TX, the control source on a dipole, energizing the water, then it interacts, inducing secondary field, which we record. Now, if you decouple those equations, so we can from that derive the electrical conductivity, inverse resistivity, and this is what we're basically producing the inversion models of electromagnetic, either MT or CSEM. Just to understand, there is a lot of kind of debate, or people tend to say, yeah, but it's low resolution. Well, it's not that low resolution because it lies between the seismic methods and the potential field methods. So you can see here, that's kind of a column of all the possibilities of EM induction. So in high frequencies, like ground penetrating radar, when you work in high frequency, you have to account for the term of the permittivity. And therefore, you have a resolution that is fairly good relative or similar to the seismic method. But we're mostly working with MT and CSEM. We're working on between 0.1 to 10 hertz. And with that, we can neglect the displacement current, and we left with only the conductive current, which kind of simplifies things. And this put the resolution between those two. So it's better than gravity and magnetism, but not as good as seismic. Therefore, we can often constrain our models with some seismic information. And the workflow is relatively simple, but just it takes a long time. So either if we have a time series of either MT or CSEM, we do some processing and get the responses, the Fourier coefficients in terms of apparent resistivity and phase, or in terms of in CSEM its amplitude and phase. And think about it this way: if there is some resistive, you will get a higher amplitude and a shorter phase, which means the field is running faster. And with some inversion modeling, we have those results of this kind of imaging. Now, bear in mind, for the entire talk, the blue colors are resistive and the hot, warmer colors are more conductive material. So you can see here that you have some anomalous conductive area that's going between these kind of more crustal regions. And here it's an example, which I'll show you later, about gas hydrogen resistivity. Now, the methods, well, coming from the US kind of work frame, we often use the Scripps instruments, and you can see that we, like you've seen in the video, we can use a control source with seafloor instruments. Could be MT or CSEM. That can give you sensitivity to about 10 kilometers on CSEM or 200 to 200 kilometers, ideally, into the upper mantle if you're using MT. Now, we can also look at in slightly higher resolution if we couple those, the source with some arrays of receivers. So we have a fixed offset, and it's running, and it has also, as you can see here, a vertical component. So it gives us a high resolution. This is pretty much can allow us to see the subsurface in high resolution data to 1 kilometer. And the same receivers, in a way, you could put them on the surface in shallow water and use it as a towed surface. And this what help us to get pretty much resistivity models through the entire kind of the areas that we're working. So we can see the sensitivity increases and the resolution kind of trend between those methods. So marine EM is useful to study different types of geological domains, as you can see here, and what are their importance in terms of tsunami, crustal thickness, hydrothermal venting, resources, and so on and so forth, if you just couple the MT and CSEM together to a specific kind of question in hand. So in this talk, now we're getting to what we are actually going to show. I'm going to show some example of previous work I've been doing that I led or been part of as a co-authorship in terms of gas hydrates, mineral resources, CO2 monitoring, fresh water, and a recent study that I was a part of on the Go Far with the team from Woods Hole about how the EM method can help us understand earthquakes. Let's look at gas hydrate. This is pretty much, I'm just starting each one to echo what we've seen, but this is the system I used for my PhD. That's the Southampton electromagnetic source. We generate electromagnetic wave on this dipole, and we have a towed receiver. You can see the components, and also a seafloor receiver. And this is, jumps ahead, this is a region, it's a Niega pokemark area offshore of Norway. And here what I'm showing you is basically the electrical resistivity superimposed on the seismic reflection section. And you can see, in terms of resistivity, you can see that the bar is linear scale, but it's very small. So seawater is 0.3 resistivity, and here we get about top of 3 resistivity in the hydrate channel, which is kind of corresponding to the seismic blanking zone that we get from the seismic reflection. So even in that small kind of amplitude of resistivity, we have a good distinction between the normal sediment water, and you can think about those kind of mid-edge warmer colors as penetration of seawater into the sediment. So obviously it will be more conductive. But yet, you can see those streams of kind of those blue areas when we know that the best hydrostability zone is lying somewhere around here. So those artifact or hydrates, and we know that under it should be free gas. Now we take that and we constrain it with some seismic information from the velocity and the seafloor, sorry. Yeah. And the stratigraphy or the structural information, and you can see that we can actually really well delineate the pipe chimney of the subvertical of the gas hydrate. It eliminates those blue regions, which we know that those can roughly preliminary artifacts, and the free gas is more constrained under the hydrate zone. And by just using arches, we estimated that the saturation of this area is about 38%. We took it a bit further, and we also used the Vulcan data, which is the towed, and as I explained, he has some more information on the vertical component, and we basically, on that region of that pokemark that I was imaging, we can actually, by coinciding lines, we can see how the high resistivity we have in that region of the pokemark. Also, we collected core sample, and we saw some hydrates in that core sample. So it gives you high resolution of the model with comparison to the seismic constraint in that sense. And then we took it another step forward to do some effective medium modeling, which is basically want to know what's the saturation, but in better ways than Archie, using the bulk and shear modeling electrical resistivity. So we take the data and we calibrated the two phases model of brine and the sediments to the core data that we took, and then we can run it, have a 3-phase with the hydrates, and using those using the velocities and the resistivities that we derive from the remote sensing, okay, and we have this kind of search table in terms of to which porosity, what we can achieve or what we will have in terms of the remote sensing data we took from our modeling. So if you dump it on that 3-phase modeling of the resistivity and seismic elastic properties, and you see the data, we pretty much can see that in a more rigorous way derive the saturation of hydrate. So we found that the hydrates, we saw before it was 38. Seismic alone predicted 32 saturation, so the effective medium modeling kind of zoomed that into a kind of 30, which is probably more robust than the other methods. Moving to submarine freshwater, this is the work I've done during my PhD, my postdoc in Hawaii. Just to tell you about the area a bit, that was a long-term project that they tried to understand why there is a mismatch between the charge of the fresh water and the discharge value in the coastline, okay? So they found that there is a 40% of mismatch. And when I got there, I was supposed to do a land kind of empty imaging, but I say, okay, so where all this water goes? Now, conventional model by USGS kind of proposed the hydrological models since the 40s that basically the water channel go through the basal water table and released at the coastline, or it deviates around the coastline. They never considered that it might be getting to the ocean. And I said, there's no way 40% will go only stay in the coastline. There must be an oceanic factor. After all, you're in Hawaii, surrounded by the ocean. So we wanted to understand, is that the only pathway? So I designed a survey to kind of go across the west coast of the big island in Hawaii. It's called the Kona coastline. Basically, we acquired 5 different types of data, and we covered about the entire kind of aquifer scale of the Hawaiian island. So 20 kilometers of data in roughly in 8 days, 12 hours per day, which is kind of a good efficiency. And I use the surface towed system that you've seen previously, when you have about 1 kilometer of tow with 4 receivers energizing the water, and the GPS is outside, so less kind of uncertainties on the navigation using this system. And give us roughly, the total is kilometers, so roughly you can trust a sensitivity to about 500 meters below the sea surface. And that gives us a way to model or see things 90 meters of water column, about 4 kilometers from the coastline, which is pretty good. And this is the final after I ran a lot of models. So as I said, the blue colors are, you can think of it here as a fresh water or the bluish colors, and the red is more basalt, because mostly basalt, there's almost no sediment, with the seawater. So you can see areas like here that it's purely, it's very conductive because there is just coral reefs that are, the water infiltrate into them. But you can see a good coherency between, this is 22 lines that I chopped them, but a good coherency that we see a two-model system, a two-layer system, that you have sort of first layer of fresh water, and then conductive basalt with fresh water, with the seawater, and another system with fresh water. And here, just in front of Kailua Kona, when we know there is a lot of lava tubes, which is 100% channel of porosity that can channel water, we got a large-scale kind of freshwater reservoir on all coinciding data, which is kind of interesting. So the mechanism that I proposed, that you have this kind of fresh water from the rain, but why would it go in 2 layers? Why is it just not releasing to the water? Because, think about it, those layers and those channels created during volcanic periods, but between volcanic periods, you have this kind of soil and low permeability layers from the ash and some of the friction. So the water can only channel in those regions, while seawater intrusions into the regions which is post-volcanic eruption in that sense. Therefore, you get this multi-layer system, which is probably going, maybe there is another layer, which I haven't been able to see, but probably around a kilometer. And then I said, okay, but what about the water column? I just modeled also the water column. In CSEM, we normally don't model for the water column because that's a fixed parameter and it's a lot of computational. But in this case, when I saw the CTDs are really varying between the values, so I modeled the water column, and you can see that in some areas I saw that there is an actual freshwater plumes that ejecting from the sea floor, if that line is the sea floor, but there is also nearby, adjacent, freshwater kind of on the surface, which probably coming from a different plume, and because the water are colder and the freshwater are more buoyant, we image them on one of the lines. And therefore, I just took that region, which is prominent, and did some conversion to salinity. And you can see here that probably just the plume that emerges from the seafloor to the water, we found that the freshwater content is about 87%. That's a lot. And think about that it's actually a renewable and sustainable system because water are always fluxing and releasing to the water. So the only place in the world that we saw that, besides Hawaii and proved, it's in Achziv Canyon in Israel. But most of the fresh water that you hear about, those are more kind of ancient water. This is a renewable active system. So I kind of reshaped the new model, updated the conceptual model, and then we saw that there's significant volumes of submarine freshwater in that area of Hawaii, and from that kind of led to continuing project to understand the entire hydrological system and understanding the biogeochemical kind of influence on the Hawaiian Islands because of those freshwater. Seabed minerals. This is a project I did when I still was in Southampton, and we went to the TAG hydrothermal event system. Mostly it's a very fluctuated, so we only use the 3D axis electric field system over the TAG hydrothermal vent. And what you can see here, with this kind of configuration, we managed to model or see most of the major extent hydrothermal vent system in the TAG area. But here you would see it working the other way around because minerals are more conductive, so those conductive blobs in red, those are supposed to be the minerals. But we also understand that the bathymetry was very fluctuated in this region, which we needed to account for uncertainties in navigation that might lead to that. That is how the bathymetry is expressed. So in the next slide, we said, okay, let's see if that affects the model. And we took that and did some forward modeling using COMSOL and then inverted it in 2D, and we realized that there is some differences that you cannot account for while doing 2D on a 3D topography. So we did some other ways to look at what will be the prospect of CSEM using just, that was 2000, started work in 2020, so it was kind of the earliest UNet conventional network system. They take the input map and derive those parameters in order to have some of the presentation of those regions that might have seafloor minerals. So it's another way to derive potential SMS or seafloor massive sulfide from bathymetry using just a simple machine learning. CO2 storage monitoring. This is a project I'm leading, supervising one of the students. It was done in 2019 in Norway by Southampton Group, the Sleipner area, and you can see that the scanner pork has a really distinctive kind of pipe channel of the scattering area where they injected the CO2 and did some different measurements like to see if there is, over time, if the CO2 kind of leaks. So CSEM was one of the methods, and students still working on the actual data, and we're getting good results, but we started with just a paper to see what are sensitivity to different saturations and different resistivity values in different scenarios, injecting that CO2 in different kind of rates. So we basically found that you started to see losing resolution only under 10% of saturation. But if you inject and you have higher saturation rates, you can actually have good constraint of the basically the reservoir that it was injected into and how it leaks upward. And then you can postulate with some modeling how it's going to be releasing from that CAPRO. So it's just an interesting way of monitoring CO2 besides the normal methods. Now the last one I want to show you, it's the one from the East Pacific Rise. This is a cruise that we did in 2022, and we had to stay in San Diego to wait. The vessel had to wait until I will finish my COVID for 2 days until I can get on board, and then we had to sail all the way for 9 days to this Pacific Rise and further on because of COVID. But that's just a detail. But the way we wanted to know the Gopher transform fault system. Now this is kind of a natural lab to understand seismicity because it has quasi-periodic system that there is some higher magnitude events above 6 every 6 years. So we were aiming to try to capture those events during the time of the survey using EM method because there was some prior seismic method. Now you can see in that region there is a lot of seismicity. It's off axis to the East Pacific rise. Now it's characterized by a rupture zone, and then there is a barrier zone. So you have a silent of seismicity. And then there is another rupture zone, and so on with the barrier zone. So understanding why between this on the main axis here, why would you have a rupture zone and a silent zone, the inhibitor, the barrier zone? And we know that there is higher quantity of breccia in that barrier zone, which is more broken, so the porosity is probably higher. That kind of absorb the seismicity, but that's not the only reason for that. So that's why we did that study. So this is just got published in Science Advances like 2 weeks ago by my colleague Christine from Woodsole. She modeled the seafloor instruments that you showed, the off-axis, 3 off-axis lines. And we show that in that region over here that coincides to all 3 of them, there is, you can see here, that conductive region that goes across the main area. Although not yet, because of some problematic data, because of the bathymetry, this is still need to be modeled. But the off-axis basically suggest that those values of conductivity are even lower than the seawater. So we postulated there's some geothermal activity here, and you get from the heat, you get some brine accumulations in those channels, and therefore you get higher conductivity. So the geothermal composition and the heat, and that higher porosity also, and the brines kind of absorb, that's what might cause the barrier zone. We also took one on the main axis, as you can see here, the main axis or the on-axis of the line 1, and we tried to model this with a deep towed. But this was, the data was collected not with the USBL, so the resolution of the sensitivity to navigation is not great. So we're getting some high conductivity at the areas, and then which could be, like those channels, could be hydrothermal venting on that area. That still didn't work. It was presented at AGU, but still it's a work in progress to understand in a natural lab how we can model and see that seismicity events or generating earthquake using EM. So, how long do I have? Just to show you like how we can move forward into domains that are important for those things I showed at the beginning. Geohazard and new sustainable resources, because those places, those things are in active boundary system, mostly in mid-ocean regions, subduction zone. And the technologies we used until now, both in industry and the academia, it was designed many years ago, and it was kind of suitable for flat sea floors, you know, in passive margins, that there is not a lot of fluctuation, and the processes were not that complex. In order to go further beyond in the new area for the new demands and the challenges that we're facing, we need to look at and design and work with new technologies. So one of the companies, PGS and OFG, donated to my lab in 2023 this kind of a long seismic streamer, but not a seismic, it has also an EM streamer. And when you couple them together, you can have a good resolution on your subsurface domain. Now, this is an inverted scale because it's an industry kind of imaging. So you can think of the red as the resistor and the greenish area as the conductor. But when you couple them together on a towed streamer, which has higher resolution, you can get good quantification of your subsurface. And this system is good for, about 500 meters of water, and you can see a few kilometers down. So this is all the gear I have now in Texas, and 6 kilometers. So we started modifying it and redesigning it to be on smaller vessel, research vessel. and added some USBL so we have a closer navigation, better navigation, and we're designing also some fresh sense that really can take other water parameters. But this will help us to troubleshoot and constrain regions like gas hydrates and fresh water on a large scale, because this system, as opposed to the other system I showed you, they have to work on 1.5 knots speed of vessel. This one can run 4.5 knots, so it can cover large areas in higher density, and we can extend the streamer to about 6 kilometers. And this will help us kind of get a better understanding of large-scale water systems. And also, there is a problem of sea level, coastal degradation, and there is collapse of the cliff, like in San Diego and Monterey Bay. So this will help us understand the coastline porosity structure of the sediment. Now, what's next? I'm taking my lab now into a different level of I believe that that's what we need to do. As besides being a scientist, I think there's it's a unique time in history that the interest of the industry and the interest of us as environmentalists and sustainable environment are merging into one. Because we both want the same thing, and we understand that fossil fuels needs to leave the door. So I'm partnering with some major companies. EMGS, that's the company I showed you at the beginning, about the EM CSEM company, and OFG, this is a company I work with AUVs, and there is a new company, it's called Quantum Marine Minerals. It's a Norwegian company that will constrain a lot of the seafloor minerals offshore Norway. So that hybrid lab that I'm developing now with my engineers and students is to have like more challenges of the sustainable human, the climate change, renewable energy, develop new technologies for the new blue economy, to have a global energy transition, to help and promote the global energy transition. And one of the ways that I'm hoping to do that, and we've been working at for a few years now, is to have more of an autonomous system that we can model Earth at CSEM with using electromagnetic, we're using an AUV. So it will give us large-scale mapping, high resolution of the seafloor of the mid-Atlantic ridges, where there are high topography and there's complex processes. So the core research of the lab, of this hybrid, will focus on those three things, geothermal, energy, seabed minerals, which are in high demands, and natural hydrogen. I don't know if you're aware, but the ARPA-E, which is the US organization that predict and design technologies for future energy, predict that by 2070, 30% of the energy budgets of the US will rely on hydrogen, but not as a gap resource, as a sustainable resource, because hydrogen, that's a pure energy. Very tricky molecule, but it doesn't have carbon. So it's a good resource of energy. Now, where all those through converge? They converge and they exist in the mid-ocean ridges hydrothermal system, which is energized by the geothermal system beneath it, deposits some minerals that needed on the seabed, and in that geothermal system there is also subpedalization process, which the byproduct of it is the H2 hydrogen, which is something that is challenging to model, quantify, and characterize. And that company I'm partnering, the Quantum Marine Minerals, they focus on the deep sea minerals for the green transition. How do we model? We build a work frame to look for minerals on the seabed, but in an extended hydrothermal vents, not active. And you can see here, this is one of the areas that we're working on. You can see that's the Muhans region. Lakis Kessel is the main area. But this is kind of bathymetry exaggerated. Also with the seismic and EM signature. So you can see a lot of resistors and conductors. So separating between what is seafloor minerals, what is hydrogen, and what is the energy, that's a very challenging task. And for that, flying with a towed system, hundreds of meters, will not be sufficient enough. So this is what we've been working on the last 2 years. Me and my engineers. And Javi obviously remembered that chapter from my PhD because he was my PhD examiner and he read the entire proposal. But I was predicting back then in 2017 that the way this future marine will need AUVs system that are flying in a different kind of configuration to have higher resolution of the seafloor, and it would need some deep neural networks and machine learning to model this high density data that the AUV gives us. And you can see that after that I worked on some project with the Norwegians and the OFG, and in 2018, 19, and we did have this system that is, we put electrodes on the AUV from Kongsberg, but not energized. So it's called self-potation method, because when you have geothermal energy, that's kind of a battery that runs electrode. And if the source is very strong, you can see that resistivity imaging. But that's not gonna be efficient enough when you're flying very high, and if the seafloor minerals are under the sediment, like 5 meters. So therefore, we need something more robust that will help us to see also geohazard in terms of subduction zone, where you have topography, and also address those areas of seafloor minerals, geologic hydrogen, so on and so forth, because you can change the configuration of the survey, 2D or 3D grid. You can change the inline, broad line, varying the offset between the receiver and transmitter. It will give you big data, which you can ideally model using AI. And this is how it's going to look like, and we already did some proof of concept on small AUVs that will have an array of AUVs with electrodes and a source that will be an AUV, but purely for a source. Now we don't need a powerful energy source because this will go about 5 to 7 meters from the water, and with a little dipole we can energize those, and using an AI kind of model, they will sense the water as like a swarm of birds when they feel that the temperature or the pressure in some areas in the air is lower, so it's better to fly from this side. Similar on a hydrothermal vent region, when the temperature, the turbidity, and some pH is lower, one of them can follow in terms of like a cumulative swarm system, and then successively charging and doing again. So that will allow us to look at large-scale autonomous, and on the fly do the data transmission. So it's still not trivial. It's still challenging, but this is how I believe that in order to came up with our answer that addresses the challenges we have, this is kind of the way that we're going if we want to go to study those complex terrain. Now there is more projects that I didn't mention here. You're welcome to go into the website and see some other about the Hawaii plume system, and something in Sicily about geothermal, and so on and so forth. And that's pretty much complete my talk, and I'll be happy to take any questions if you might have. Now, it's a lot of information, but I try to give you an overview of what this method is about in a way and what we can use it for. Yeah, I can hear you.
Okay, I'll sit down then. Eric, thanks for the talk. So you presented some hydrate concentration estimates, but I guess resistivity is dependent on either several phases in the system, like seawater, concentration of gas hydrates, concentration of free gas.
I just modeled the chimney itself when I know the actual resistivity of it. You're right.
I mean, also porosity changes throughout the system.
Yes.
So my question here is, how accurate are those hydrate concentration estimates?
Okay, so the benefits of...
What's the uncertainty range on those estimates?
Oh, the uncertainty range is about 5 to 10% in terms of which is much better than the arches, because the effectiveness of the effective medium modeling is that we build a microstructure of that composition at the time. Think about it as a box model. We take the seawater with their bulk and density, bulk and shear modeling, and the resistivity of shearwater that we know from the CTD. We incorporate it with the sediment mix that we have over there. And over there we had a mixture of 45 quartz, 55 clay. So we accounted them as one. So that was our two phases. And then we injected the hydrate. So in terms of that, you know, the arches has a lot of empirical relationship. But when you build a box of your composition or what you're trying to model, each step at a time with all its parameters, that reduces the uncertainty. But the key critical step is, as you've seen, I calibrated the 2D model, which means the sand or the clay and the quartz with the seawater against the core sample. If we didn't have core samples, which I didn't know what would the resistivity will represent, which kind of porosities, range, and velocities. So I couldn't have done that. But once you have the data and you calibrate the 2D model on the data with the data, then when you insert the hydrate, you can see what hydrate saturation needs to be there in order to justify the resistivity and the velocities that you see from the remote sensing. So in a way, as every method, it has the uncertainties that come from the remote sensing. But the effective medium modeling is much more rigorous in terms of quantifying versus arches or just doing it from velocities. Yeah, it's complex. That's why I didn't get into that too much. But yeah, it's.
Any other questions? I have one. When you talk about the seafloor massive sulfides, do you think that's going to be at some point economically viable, the exploitation?
Absolutely. I will give you two examples. I've been going with the Japanese through the OFG since 2016, multiple times to Okinawa. They have a lot of volcanism and hydrothermal system, and the Japanese, as you know, they're very rigorous, and they just released a note about a year ago that they have discovered the highest amount of seafloor massive sulfide, and they accounted for the tons and the potential economical value of it. So now they're in the stage of building drillers and building the mechanism, the infrastructure to excavate that. Same with the Norwegians. If you talk to the Norwegians and companies and the Norwegian offshore department, they kind of realize that oil and gas, that's the past. They're not investing in it anymore. They're not interested in that. They will still sell what they have. But we've been, me and my engineers, to 5 campaigns, long-term campaigns with AUV, basically doing a reconnaissance of the entire mid-Atlantic ridges in front of Norway to kind of detect potential SMS, because we're just increasing our needs for rare critical minerals. And the only volumes that there is today is in China on land, and it's not enough. So you'll see progressively how countries are going into that region, but it still needs to kind of account for the impact, environmental and the biological system. Anyway, that's kind of my motivation to work with the industry, is to be the gatekeeper, to say, okay, this is not doable, or this is not environmentally sustainable. We need to think of a better way. We need to be careful, because if you're just going in and replacing one damaging thing, as we did with fossil fuel, with another damaging, we haven't learned anything in that sense. But I'm confident that in the next 10 years, most of the seafloor minerals will come from the ocean.
Okay, I don't think the same, but anyway. Any other questions? I have a final one. When you were showing those arrays or of AUVs, you included the source in one of the AUVs, but it's not going to drain too much power?
So normal source that you know and I know of, you need a long dipole with a lot of power. Why? Because you're flying very high, okay? Now if you take an AUV and you take all the nice payloads and you just keep obstacle avoidance, so just a DVL and INS with the USBL kind of acoustic modem, and a battery source, you can see here that you need just a very little dipole. And that's kind of, I even exaggerated with 20 meter, I can do it with 5 and 10.
But this is going to be for very shallow studies.
Yeah, but like, no, not necessarily, because you're energizing the seafloor, and the receivers that are now untethered, they control the offset. They will see the depth. It's all about the coupling of how much you energize. You're right. It's not like sending 300 amps that we normally do now, but think about the linear relationship. If you have 300 amps from 100 meter altitude or 20 amps from 500 meter altitude, you'll get a better coupling, and the electromagnetic wave will propagate and will energize those UVs for kilometers behind. So this is kind of concept, this kind of simple modeling of skin depth.
Thank you. Questions? Peter.
Thanks. Nice talk. I have a question related to the fresh water. So in Hawaii, is there any plan to use that water? So I think it's more feasible or more interesting to look for this fresh water that it's going to be mixed with seawater than looking for deep sea minerals. But I'm curious about the potential use of this fresh water in these islands.
Yeah, so Hawaii is a very special case. They also had the geothermal energy, and they closed it down because the Hawaiians and that the nature and the culture is there is to not harm and not touch the environment. In Hawaii, it's my colleagues and our colleagues, Amir, had got a position there to do the same kind of studies all across the oil islands. But this is more in Hawaii will be in a way to understand their biogeochemical systems and to understand their sustainability. It's in order to manage, because all of Hawaii water is from drilling on the island. So to manage their water level, water tables, and to see that they're not affecting the ecological system. But that's Hawaii. But if you take other places like Cape Verde, Galapagos, which are less sensitive to those environmental questions, I believe it could be a viable resource. There is an Italian company that's already harvesting the plume water. But think about it this way. When you drill in the mountain kilometer, that's a lot of, which is elevation of about a kilometer. You need a lot of energy to pump the water up. Those, what I showed you in the plume, those are residual water, which means they passed all the ecosystem. They're offshore. They're basically all what the system basically accounted for, and that's the residuals of that. So if you harvest them over there, that's in high hydrostatic pressure, so you don't have to invest energy, and you know that it's not going to affect the upstream biological system like the cesspools they have over there and all the farms. So I believe it might be a valuable resource to islands that are really in need in water. Even I got an email once from South Africa. They're really interested in that because there are days that they're not allowed to use water. So
I was thinking more in if you need to install a desalination plant to create fresh water instead of taking the seawater out of the coastline. Yeah. So you send a pipe with some pumping system, and then you pump water that is very fresh, and exactly. Then the energy you need to
exactly. That's kind of the entire motivation, because desalination, they need a lot of energy, and you have still the problem of brines, which if wherever you dump them, you change the mineralization of the environment. So yeah, but in a while, I don't think it will evolve to actual a resource that they will use. It's more to understand their systems.
Yeah. The use of brackish water. If you use seawater, you can only extract 45% of fresh water, and I always find it ironic that they call about brines when as the outflow from the desalination plants, when that includes coagulants, which are metals, includes chlorine, that there is a pre-chlorinization process and other chemicals, and that's the brine.
Yeah, and you're right. And when I went to Hawaii, I asked them, why don't you just do distillation? I come from Israel, which in the 60s, we already kind of mastered the distillation because we realized we're going to be dry. And they told me, no, this is not even an option that anyone will propose to the Hawaiians. So they need to find alternatives, or at least understand the systems.
And with brackish water, you can extract 95% of fresh water.
Yeah, it's just, if you have 87, just a small filter, and it's good for drinking or good for farming and agriculture.
Yeah, and the power requirements are also less, so there is a less impact on
exactly.
Which right now the desalination plants are very dirty. So.
Yeah, there is one that says a low energy in offshore San Diego, I think, that is really high end and doesn't require, but it still has the physics is the same, and the brines, you're right, is coagulants.
Anything else? No. Well, thank you, Eric.
Thank you. Thank you for coming.